Only 3. Okay? So we're getting to exercise 3. This one we will be doing, and then I have good news after this wonderful little problem. Okay? There is a quiz tomorrow. Unless we have school and then you take an online quiz. Just kidding. So, a cylindrical space station of radius 12 meters, mass of 3,400 kilograms, has a moment of inertia of 0.75 mr squared. Retro rockets are fired tangentially at the surface of space station and provide an impulse of 2.9 times 10 to the 4th Newton seconds. Yeah, you guys missed impulse actually quite a bit on the quiz I was grading. I was surprised, really surprised. Okay, that's what bumpers are for. Okay, they increase the amount of time that you are tracking on that object, thereby decreasing the force of the impact. Okay, I was surprised by that, and that wasn't just you guys; it was all the kids. So don't feel bad. Okay, now you know. So,
no, pick it up though.
I'm sorry. Okay, so. A, what is the angular velocity of the space station? Okay, what is the angular velocity of the space station? So we're going to use a few formulas that you know. Okay, first formula. You know, tau equals I times alpha, correct? Okay? And I'm giving you that one right now because we went over that in lecture today, so that should be fresh in your mind. Okay? Something else that you know. You know tau equals what? What's this equal? We just went over a problem I had it.
F times D.
F times D. You know tau is force times the lever arm. Okay? Have we related this to angular velocity yet?
No.
What is angular velocity? What letter?
AT.
Greek W, which is omega. Okay? So it's related. We can assume our average. That's fine, because we're not specific in terms of not constant acceleration or anything like that. So that's fine. Alpha equals omega F minus omega I over delta T. Which is great to have delta T in there because impulse is given by the formula F delta T, right? Without delta T, you can't have impulse. Okay? The force isn't acting over a given period of time, it's not going to have impulse. So, it's acting over a given period of time. So we're going to use that. So we're going to use these to solve for our omega. Depending on how you read this problem, you can either have initial angular velocity or it's going to be stopping, one or the other. Okay? Either way, that impulse is going to either start it or stop it. Okay? So you can make that the omega I as 0, or you can make omega F 0. Really doesn't matter. Okay, we're going to substitute everything in, and then we'll hit that. Okay? So, we got her. Thank you. So, let's plug things in. Ft equals I times alpha, which is omega F minus omega I over delta T. So, all I did was I substituted in the equations into tau equals I alpha. You know impulse is F delta T, so we need to get F delta T together so we can plug in our value of impulse. All you do there, you multiply by delta T, you get F times delta T times D equals I omega F minus omega I. Okay? All I did was I multiplied by the delta T. That gives me my impulse times the lever arm equals my moment of inertia times my angular velocity. Final explanation. We're going to assume that's going to We don't have to worry about this. Let's assume that reaches 0. That's your initial. Okay? Now this impulse is going to create that momentum change. So you can solve for your final angular speed, right? You can solve for it. Divide by I, divide by I, and omega f finally equals f times delta t times d over I, which is your impulse times your lever arm divided by moment of inertia. Do we have everything? What are we missing?
I don't know. Okay. Right. I don't remember what the problem was.
What are we missing? So let's look at it. Okay? We're looking for the angular velocity. Do we have our impulse? It says in the problem 2.9 times 10 to the 4th newtons. Okay? We do have our impulse. Do we have our lever arm or our radius?
Yes.
Yes. Do we have our moment of inertia? We don't have the actual number.
It says the other one has moment of inertia 0.75 units.
Yeah, still two variables in there. I equals 0.75 times the mass times r squared. 0.75 times the mass, we have 3,400, which is kilograms, times the radius squared.
Get to the nitty-gritty. This is the fun part. This is the context of the problem.
Exactly. The end of the problem. So,
We'll find that out.
your moment of inertia will equal 367,200 kilogram meter squared. And you can just plug everything in now. Okay? And then we're done. Yeah. So this is 29,000 Newton seconds times the lever arm of 12 meters.
How is the force really moving per second?
That's force times time, which is impulse. That's why it's Newton seconds.
Oh,
Okay, that is the impulse, Newton seconds. Then you're done. Okay? Any 30-second questions? Real quick?
You said you had good news. Please.
Yes, coming soon after these messages. Any 30-second questions? So start, come back to it, try it on your own. Okay, make sure that you write down these equations at the top, and then you can solve this problem. Okay? If you don't have the equations, you're not going to be able to solve it. If you have the equations, you can. Okay? So, here comes your good news. Here comes your good news. You get to put X across this problem. We are not going through this problem. Don't worry. Okay? This wasn't so bad. It was
8.9?
huh?
8.9?
8.9. No go on 8.9. Okay? We're now going to go through the Olympics. Okay? Take a mind up for your break on your mind. There's more good news. Wait for it. Okay? I got other amazing news level. There's more good news. Okay? So we're going to go through the Olympics real quick, and here's what happens. You get a list of two different objects. Okay? And you need to tell me which one has a higher moment of inertia. So let's think about it. Moment of inertia depends on mass, and we assume both objects have the same mass, that's fine. But then it also depends on where that mass is located. The further out that mass is located from the axis of rotation, the more the moment of inertia, right? Okay? So that's what you need to be thinking about. Does it have a high, does it have a low moment of inertia? Also, you can So a hollow cylinder and a solid cylinder. Think about it for a second. Is the mass located in a hollow cylinder? Is there any mass located in the middle? So there's really no mass towards the axis of rotation. All the mass is towards the outside. So that's going to have a high moment of inertia. The solid cylinder is going to have a lower moment of inertia because it will have some of that mass more centrally located. Okay? Using your equations, you would also come to that assumption because hollow cylinder, the formula is I equals mr squared. In a solid cylinder, the mass is half mr squared. Okay? So it's actually half of what the hollow is. Okay? So you can use your formulas or just think about analytically what's going on in the problem. Second question in the Olympics is the hollow cylinder and the sphere. Which one has more moment of inertia?
The hollow cylinder.
It would be the hollow cylinder. Because the sphere has more mass inside, okay, closer to the axis. A hollow cylinder, if you look at your equations, is I equals mr squared. A sphere, 2/5 mr squared. Okay? That's your equation for a solid sphere. Look at your equations if you're struggling with these. This one's really difficult. You probably you could think about it for a second, but easiest way to do this one is to look at your equations. A sphere is 2/5 mr squared, and a solid cylinder is a half. So the cylinder would have a higher one, correct? Yeah.
This is actually this one.
The cylinder would have a higher momentum by 0.1. So this one, it depends if you're assuming that the Mountain Dew is going to be a baton or not. I don't care. I'm not going to give you these next two because I don't like them. If the Mountain Dew is a baton, then the solid cylinder, you would have to run some calculation because the baton is going to use L, even though it would use in this case, depending on where you're rotating. If you're rotating in the middle, it'd be 1/12. If you're rotating on the outside, it's 1/3. Yeah, that's also a question. I don't know. Okay. So the next two, I would say don't worry about. Okay. I'm not going to ask you about Mountain Dew. Sorry. My wife will be so sad. Here comes more good news. You ready? You can X out all of angular momentum. That means we are not doing angular momentum.
At all?
At all. Which means, guess what? No, not even close. Page 294 on your homework is no longer homework. Page 294 on your homework is no longer homework. Okay? Make sure to write that down, make sure you don't do it. The reason is because I had to shorten it a little bit. I'm not even going to get through everything today, but I did have to shorten it a little bit just to help out, okay, with all the material, stuff like that. So if I can skip one whole topic, I will. That's why I did simple machines anyway. Okay? 8.13 on the next page. That is about angular momentum. That's one of the examples we were going to go through. You can X that out. That is over angular momentum. Okay? I secretly deleted tons of these already, so these are just the ones that we didn't have time for. Okay? Now, the reason why I X'd those out was because I think that this is more important for you. We will be dealing with the kinetic energy of this rotational motion. An object that's rotating will still have energy when it's rotating. Because it does. Yeah, or if we're just standing in a high place. Okay, we still have energy. So, we're going to have to be able to calculate that rotational energy. That's given by half I omega squared. And that's going to be the equation that we use for that. Okay? I'm going to run through, I have about 3 minutes. I'm going to run through that first problem. And the second problem we're going to save for tomorrow. Okay? After the quiz. So,